Today we're diving into Boyce Codd normal form, often abbreviated as BCNF. It is a sophisticated database normalization technique. Consider it a stronger, more refined version of the third normal form, or 3NF, designed to tackle specific types of data redundancy. So, what exactly is Boyce Codd normal form? A relation is in BCNF if and only if for every non-trivial functional dependency, denoted as X determines Y, X is a superkey for the relation. In simpler terms, for every dependency that exists, the determinant, that is X, must be a superkey. BCNF takes normalization a step further than 3NF, eliminating all redundancies that are based on functional dependencies. By adhering to BCNF, databases can avoid certain anomalies that 3NF might still permit. Let us discuss the key differences between BCNF and 3NF. In Boyce Codd normal form, for every functional dependency X determines Y, X must be a superkey. It eliminates all redundancy that is based on functional dependencies and is stricter than 3NF, but it may require more decomposition of tables. Whereas in third normal form, for every functional dependency X determines Y, either X is a superkey or Y is part of some candidate key. It may still contain some redundancy and is less strict than BCNF, and it preserves all functional dependencies. Let's consider a student course registration table with columns for student, course, and instructor. In this example, Alice is taking database with Professor Smith, Bob is also taking database with Professor Smith, Charlie is taking networks with Professor Jones, and Alice is also taking networks with Professor Jones. The functional dependencies in this table are: student and course together determine the instructor, and the course alone determines the instructor. The second functional dependency violates the BCNF. For our relation R, with attributes student, course, and instructor, the candidate key is student and course. This combination uniquely identifies each row in the table. The functional dependency course determines instructor violates BCNF because course is not a superkey for the relation, yet it determines instructor. In simpler words, knowing the course is enough to determine the instructor, but course alone isn't enough to uniquely identify a record in the table. This design suffers from several problems, including redundancy, where instructor information is repeated for each student taking the same course. This leads to update anomalies, where changing an instructor requires updating multiple rows, and insertion anomalies, where you cannot record a course and instructor without a student. To achieve Boyce Codd normal form, we need to decompose the relation. First, we identify the BCNF violation, which is the functional dependency where course determines instructor. We split the original relation into two new relations. The first relation, R1, consists of course and instructor, with the functional dependency that course determines instructor. The second relation, R2, consists of student and course, with no non-trivial functional dependencies. The relation R1 has course as key, which determines instructor. The relation R2 has student and course as key. Here are the resulting tables after BCNF decomposition. The first table, R1, relates course to instructor. For example, the database course is taught by Professor Smith, and the networks course is taught by Professor Jones. Note that there is no redundancy in instructor data. The second table, R2, relates student to course. Alice is enrolled in database, Bob is enrolled in database, Charlie is enrolled in networks, and Alice is also enrolled in networks. There are multiple benefits of using Boyce Codd normal form. It eliminates redundancy by removing all redundancy that is based on functional dependencies, resulting in more efficient storage and reduced data duplication. It prevents update anomalies by ensuring that data modifications only need to be made in one place, preventing inconsistencies during updates. It prevents insertion anomalies by allowing insertion of data without requiring the presence of other unrelated data, making the database more flexible. Finally, it prevents deletion anomalies by ensuring that the deletion of one fact does not result in the unintended loss of other unrelated facts. One of the limitations of Boyce-Codd normal form is the dependency preservation issue. BCNF decomposition may not always preserve all functional dependencies from the original relation. This can make constraint enforcement more complex and potentially impact query performance. You should use BCNF when data integrity is critical, when storage efficiency is important, when update operations are frequent, and when redundancy must be minimized. Alternatively, you should consider 3NF instead, when dependency preservation is critical, when join operations are expensive, when query performance is the priority, and when the application is read-heavy. In summary, Boyce-Codd normal form is a stronger form of 3NF that eliminates all redundancy that is based on functional dependencies. A relation is in BCNF if, for every non-trivial functional dependency, X determines Y, X is a superkey. BCNF decomposition may not preserve all functional dependencies. BCNF prevents update, insertion, and deletion anomalies. The trade-off is between data integrity with BCNF and query performance with 3NF. Next, we will delve into the fourth normal form, also called as 4NF, fifth normal form, also called as 5NF, and denormalization strategies. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.